Welcome back to Math Club, and this time we're going to go a little more into what we were discussing last time. So, we had the equation y equals x squared, right? That's basically what we were looking at. We had it as x of t equals t squared, but this is basically the same thing, okay? Instead of looking at it on a graph and looking at all of the properties of it, in like trying to find slopes at certain points and stuff. Instead of doing all that, let's look at a box, a big old square, right? It's an x by x squared, meaning the area inside is x squared. Okay, now let's change it by some tiny amount I'll call dx. Now by dx, you will assume it means approaching zero. It'll never actually be zero. It'll be some finite value that's extremely small and close to zero. Right? Right here would also be dx, right? Because we're also changing x here. And this right here would be another little square that we added on. So what's our change in y going to be? Our tiny change in y going to be in this case? Well, it's going to be all the area that's added on, right? Because y is x squared. This is the area, and we're looking at the change, which is going to be all of these little areas. This length right here is going to be x. This length right here is going to be x. So I have x by dx, x dx. So I have another one that's x by dx. So it's x dx. And then adding on to that, a little square that's dx squared. Okay? Now let's divide by dx on both sides. So dy dx is then going to be, well, x dx, right? These become 1. That becomes dx. So I have x plus x, which is 2x. Then on that, we're adding dx, but dx is going to 0. And when we're adding that on, it basically does nothing. So, it basically does nothing. Nothing really happens because of it. It's not really doing much. So, we can just ignore it. Okay? So now, we have the same exact thing we got from before, right? From y equals x squared as we got from x of t equals t squared. Got the exact same thing. So maybe this would work for y equals x cubed as well. So let's go ahead and look at it. Right here is one face of the cube. Go back, create another face of the cube. Right there, we have our cube. It has a volume, or it's an x by x cube. Now, the volume of this cube, y, I'll call it, y is going to be x cubed, right? Now, let's go ahead and look at it when I add on just a little bit, right? I'm adding on just a tiny amount, some amount that's approaching 0, but never really reaches it, right? We're adding that tiny amount to everything here. So, then there'd also be a little amount on here, right? I think you get the picture, right? And all of these have a sort of depth of dx, okay? So, let's make sure we have all of the pieces and the parts. Okay? Now, here are all the parts. There's 3 different faces right here. And each of these little face boxes, I'll call them, they each have an area, a volume of x squared dx. Can you see that? The depth is dx, and each of them are x by x, right? X by x, okay? So that's x squared plus times dx plus x squared times dx. And then on that, we're adding another x squared times dx for each of these. Okay. Then next, we have a little cube right here. That's dx by x. So we're going to have x dx squared. And there's also 3 of those. I'll just multiply it by 3. And then there's this little cube that you can barely see in my drawing, but it's there. And it has a volume of dx cubed. And this right here is our change in y. Okay? So our change in y, it's going to be 3x squared plus 3x dx squared plus dx cubed. Okay? Now let's, dx right there. Dx plus. Okay. Now let's divide by dx on both sides. Okay? That becomes 1. That becomes a dx. That becomes a dx squared. Okay, now I have dy dx equals 3x squared times 1, which is 3x squared plus 3x dx plus dx squared. Now, we know that dx is going to 0, and we're adding this on. So, really, it's not going to do anything either. So, whoop, got rid of you. And now we're left with this. dy dx equals 3x squared. So if we look back at our original formula for our change in y over change in x, right? It's going to be y of x plus dx, or x plus some change in x, minus y of x divided by your change in x, right? Replace all of these capital deltas, Greek letters, by d's. That signifies that all of these are going to 0, right? Every single one of these are going to 0. This is our new equation. And if you plug in y as a function of x equals x cubed, you will get the same answer, this right here, as you would get from this cube method. Basically meaning this is all rooted in shapes. All of these derivatives and all of these slopes, they're rooted in the shapes. Now I'm going to give you a formula that I'll try and explain. If y is x to the n dy divided by dx is going to be n times x to the n minus 1. Okay? You can kind of see this, because if you plug in x plus dx to the n, you get x plus dx times x plus dx times n times, right? N times, really what you're doing, you can do you have to first multiply it there, then you have to multiply it there, then you have to multiply there. Let's follow this track. Dx times x, and then x times that x times that x times that x. That's going to be, well, dx x to the n minus 1, right? Makes sense? Because I'm doing dx, that takes up one spot, but every time afterwards, I'm just multiplying by x. On that, I can also do x, and then dx, and then the same thing, right? That's also dx, x to the n minus 1. But then I could do x times x, and then times the dx, and then all the way down. And then I do that n times for each of the dx's, right? Then I get n dx, x to the n minus 1, right? Then I also have x to the n, right? Then I'm adding a bunch of other stuff. And then off of that, I'm subtracting x to the n, doing the derivative formula, and I'm dividing by dx, right? So these cancel out. That is the only term with dx in it. So that's the only term that has dx in it. This gets us to nx to the n minus 1. On that, we're multiplying something by dx. On that, we're multiplying by dx squared, right? We're adding a bunch of stuff. But in the end, all of these are going to go to 0, and we are just left with n x to the n minus 1. So that's going to be the derivative of y in respect to x. That's how we say it. Derivative of y in respect to x. That's what it is. So I hope you get an intuition of this. And another rule that we might not know. The derivative, this is another way you can write it, of some c x to the n, of some c times some function of x, okay, in general. It's the same thing as that constant times the derivative of that function. Okay? So basically meaning if I'm doing y equals 3x cubed, I can find out what dy dx is. It's going to be 3 times the derivative of x cubed, which is going to be, well, you can imagine the 3 hopping down in front of the x and then subtracting 1 off of it, right? 3x, right, to the 3 minus 1 is 2. And you get 9x squared. And if I were to take the derivative of that, it's going to be 9 times the derivative of x squared. Put that 2 right down in front. You get 2x to the first, right? 2 minus 1 is 1, which gives us 18x. Okay. Now, another important fact to realize is that the derivative of, say, like 5 is 0. Now, this is because it's the same thing as the derivative of 5 times x to the 0, assuming x is not 0. And then you get, well, 0, bring it down. Then I have 5 times the derivative, 0, bring it down, 0 times x to the 0 minus 1 is negative 1. Well, that 0 kind of wipes everything out, wipes that out, we get 0 out the other end. So constants, like 5, their derivative is just 0. And it kind of makes sense, right? Because we were talking about slope before, and we look at y equals a constant, right? Right here is 5, y equals 5. Well, you can see that if I take 2 points really close to each other and I look at the line that goes between them, it has a slope of 0. So, yeah. That's the idea.